Hello everyone, welcome to this introductory course for differential geometry of curves and surfaces. My name is Tobias Dietz. I'm the professor for your course. Over there is Tong. He will be the teaching assistant or one of the teaching assistants. Before I start with the mathematics of the course and I would like to, or also the organization of the course, I would like to give you some general picture of what you will experience in the course, what the course will be about. And I would like to do that by more or less give you some ideas about what each of these words in the title means. So curves and surfaces are the simplest one to give you some intuition about because you know them. Like curves, for example, could be something like this. So it's like some one-dimensional object, and you know, like one-dimensional objects in the 3D, they're like curved and bent, and you can have like some cool figures of them. And we will study these kind of like geometric properties of like how much is this curve bent, and like for example, how often does it turn around. Like if you have like some charging cable, then you notice in your backpacks they always turn to be like mangled like this, and then you have to figure out how to get them untied. So things like this will be discussing how tight you are like curved and like how you're bent. So that's like for curves, and similarly for surfaces, you also have like some intuition about like that's two-dimensional objects. For example, here the surface spanned by the umbrella, and you also know that like they can be curved and bent, and you can like change them also. Like so for example, this one is like slightly less bent, and now it's almost straight. So these are the kind of things we want to study, like curves and surfaces. And then we have like two more words which give us some idea of how we will study them. The differential, or like maybe the geometry first. The geometry tells you what kind of properties we are interested in. In that case, really we are like interested in geometric things like curvature, and something that is called torsion, for example, for a curve. That will be like something that we will study, like how much it is like curved, for example. Also, for example, how many holes there are in a certain object and stuff like that. So that will be is like what is encoded in geometry here. And the differential gives you an idea how we will study that, namely with methods that you already know from calculus. So differential means differential calculus, essentially. And that gives you an idea how we will study these curves and surfaces, namely by methods like taking derivatives of certain objects and integration. So that will be like what differential is about. So that gives you a rough idea of what the course will be about. But what I want to motivate a little bit more is like, why should you care? Like, why should you sit here and not just because someone thought like it's very handy that you learn something about differential geometry and now you sit here, but really, why would you care about that? So that I would like to motivate a little bit further. And let me start with like maybe some story. Like look forward like 10 years from now, and you're bringing your small child to bed, and like it's asking like, hey, Papa or Mom, how did you learn like back then, like the mom, like how did you met them, like your partner? And then you think about it, and you say like, oh well, there was this one differential geometry course that was really, really tough, and like I worked quite a lot, but that means also that I had to spend quite a lot of energy into doing the homeworks, and there was this very nice lady, or this very nice guy, that I continuously talked with to make the homeworks together, and then we get like in contact, and like, yeah, that was really nice, and at some point, at the end of the course, I asked this guy, yeah, would you like to go out with me? Like, I know this really nice Italian restaurant in the center of Shanghai, and I would like to have a really nice date with them. So you can imagine, like, you go out, and yeah, you look very deeply into each other's eyes, and you have like this pizza in your hand, and yeah, like it's an amazing date, right? Yeah, well, that's like your imagination of how it went. Like reality might look like different, namely that you don't think about physics or the geometry. You were just like too focused on the eyes of your partner that you went out to date with. And what happened is that you hold your piece of pizza and it bent over like this. And like all of the nice juice of the pizza and like the tomatoes all fall under of the nice robe and the dress of your partner. Yeah, so like the date went not well, but for somehow you still ended up getting married and having kids. So something went right. But I will not give you any advice on dating. That's not my expertise. But I will tell you something about how you can prevent like these kind of things happening, that your pizza is bending over. So at some point of the course, we will really look at like how you should hold a slice of pizza in a way that it's not bending over and that you don't have like these problems with, yeah, like that all of the nicey juicy things are flowing down from the pizza slice. And you can already imagine like why that is something that we can look at in this course, because it's clearly something where curvature plays a role, right? Like if it bends down, then it's more curved. So like the methods that we develop in this course will be perfectly suited to answer this question, like how should you hold a piece of pizza so that it doesn't bend over. So that's like, I think like the most applied application I can give you of like this course. But there's a lot of different ways you can think about differential geometry and its applications. And I would like to ask you first, because I think that's quite different background. So who of you have some applied mathematics major, or like studying towards applied mathematics? Just raise your hand if you think that applies to you. Like, so no one is doing something with applied mathematics? Okay. Who is studying something more like in physics? Like you can take that a little bit broader, like something in physics. Who is doing something in physics? Just raise your hand if you do physics as your major, or you like physics the most, if you don't have not yet decided about a major. Like there's no, okay, like what are you studying, guys? Do we have some engineers also broadly? Okay, just raise your hands if you're like an engineer, or like you like engineering the most of your subjects that you had. Could you translate that maybe? Because I think okay, good, good. And like, what about physics? Okay, so like a little bit more of physics. Engineers? Okay, so quite a lot of engineers. So that's what I thought. And what about computer science, informatics? Some people there? Okay, so what you already saw is like that quite different crowd. You have like the corner over there is like more applied mathematics, and you have some physicists, and most of you are engineers. So why would you care about like the differential geometry? And that's what I want to motivate first. So for those people that are more into mathematics, there's like two different things that you can ask, or what mathematicians are looking at. It's like the typical questions that you think is, for example, what kind of shapes admit a certain structure? Like how can like they bend, or like what kind of possible configurations you have there? And then there's like this question that you already saw, or what you can imagine, for example, if something is really bent, then it turns over quite often. So there's like this question of like some local things that you can measure, for example, how something is bent, connects to something that has like more like information that you need to know that, like the whole curve for, like for example, how often it winds around something. So there's this connection between something local and some global properties, which are very interesting from a mathematical viewpoint. And then there is some questions about what kind of invariance do we have. Like, for example, I give that example of like of the umbrella. You can like slightly change the umbrella, and the curvature clearly changes as well, so it gets more flat. But is there some kind of invariance that tells us like how a certain object behaves under deformations, and what does it stay constant, or what does change and what does not change? These are like other questions from a mathematical viewpoint. Yeah, and these ones lead, for example, to the classification of that there's clearly a difference between objects that have 0 holes, 1 hole, or 2 holes, and like a few other things. So that will be, for example, something that we also discuss in this course. For the physicists, which I think was sitting here and a bit in the middle, there are a lot of things in physics where differential geometry is very helpful. The first thing is that just like your problem that you look up, that you are interested in, just might happen to place, being placed on something that is curved. For example, if you look at some particles that move on the Earth, then you have like automatically the curvature of the Earth, and that plays like some role of kind of the problems that you would like to study. So like just because like the spaces are curved by themselves already gives some interest. But even more like what is like, I think like the story about the modern physics is that most of the modern physics is now related to some geometry. And for example, we have like the example of general relativity, which tells us that the mass an object has curves the space and space-time of our universe. So that's like very fundamentally. We will not quite go as fast to study that in this course, but we will in some way provide the tools that you can go on in your further studies to really look at general relativity. And then there's like something which is like where geometry is also very helpful, and that's particle physics, where people realize that like the language that we use to describe particle physics, so it like, for example, where small particles collide, actually also has a very beautiful reformulation in geometry. And again, like what we will discuss in this course is not really that kind of geometry, but we will build up to it and like give you the tools that you can like further in your studies learn more about like gauge theory. So that's like two examples where in physics geometry is really important. I think there are no one raised your hand, but maybe there are some people that are like interested in computer informatics. You have in computer science, geometry is also very often used. For example, if you have pictures or some videos about self-driving cars and how they recognize the environments, you also have to recognize certain objects. And what you usually do, or like the classical methods at least, went back to, okay, how do you recognize certain curves and how they are bent, and then reconstruct the environment based on that. So that's like, for example, object detection. Also there's some cool stuff now with machine learning. There's a whole subject that is called geometric deep learning, which is like really been happening. So there's a lot of applications also to these very modern fields where geometry is like playing an essential role. And then most of you were some form of engineers. And in engineering, also like differential geometry can really help you to study certain problems. One of them would be, for example, robotics, or more general, some constrained dynamic systems that you would like to study. For example, if you can like imagine like a robot has like one arm and then a second one, and it can move this arm, so it has like somehow like a sphere or like some rounded object that it can reach, and then based on each of these arms you have a second sphere. So it's like quite complicated geometry that interacts with where possible spaces could be. And then you have like questions like, how should I move my arm so that I reach a position in the best way? And that's also like related to geometry and like curves and surfaces. Then there's some other objects, for example, the elastic tensor that you define that gives you how much stress is in a certain material if you bend it. And it's like something that is very easily can be described using the geometry that we learn in this course. And it's also very natural. Like if you have like a straight thing, then there's almost no tension. But if you bend it, then you increase the tension in that object. So it's like these kind of questions are usually really important if you want to understand how much stress on a certain point or in a certain location is giving that you bend your object. And one application of that is that we have like applications to architecture, where you actually use that you can bend certain objects and then get like certain nice properties. Usually it's that if you bend them, then that gives you some structural properties or some enhanced stability kind of results. So these were, for example, examples of the Munich Olympic Stadium. That was like a time where people really were fascinated by like this kind of geometric architecture, which is like called a minimal surface. So that's like a surface that is described by a certain equation, and then they really use these solutions to build like architecture and kind of roof designs. So now I would like to ask like the two people that had like Red Bull. Are you finished already with yours? Because I need them now. Awesome. Thanks. So like you probably think like, why do I ask like for people to drink the Red Bull? Just like a test for like your intuition. How much pressure do you think I can put on top of a Red Bull bottle without it breaking? Like I put it like say, put it here, and then what kind of weight should I put on there before it crumbles down? Do you think I can put like, for example, do you think it holds the water bottle? Like maybe, or do you think it goes down? So who thinks like it's about 1 kilogram of maximum? If I put more than 1 kilogram, then it will crumble. Who, just raise your hand if you think it's below 1 kilogram. So you all believe it's more than 1 kilogram, okay. Okay, you're testing that already, so I have to get that away. So it's more than 1 kilogram. Who think between, say, 1 kilogram and 5 kilogram? It's more than 5 kilograms? 5 kilograms is quite heavy already. Yeah, so like before you just put like 5 kilograms, you put a plate in here and then it crumbles. At what kind of weight do I have to put on there so that it starts? Okay, so no one thinks it's below 5 kilograms. Okay, one guy over there thinks it's below 5 kilograms. So keep 10 kilograms. For reference, that's like a whole bucket of water, like a whole big bucket with water, and I put it on one of these small little things. You think it's like crumbles? So it's like a few more fingers between 5 and 10 over there. Okay, 5 and 10. We have between 10 and 15. Who thinks it's between 10 and 15? Okay, so that's more. So now we are at 20. That's 2 complete buckets of water. Who thinks it's between, okay, that's a bit more. The rest thinks it's more than 20 kilograms? Okay, how much more do you have? What is the maximum you think that it holds? 50? Okay, 50 kilograms. Okay, I would say maybe we do it like the test. Like, but the problem is, like once you kind of put like a few of the things inside where you just like dent a little bit. These are really stable. Chinese quality. Okay, last time I did this with like Coca-Cola and it really was like, but okay, like Red Bull seems to be stronger. Okay, yeah, like presentation effect, it doesn't work. My point was, but like apparently it doesn't work with Red Bull, is that once you dent it, then this whole stability goes down. So yeah, we maybe need like a few more people to test that. But like the point is really like that certain curvature in one direction gives you a lot of stability, and that's what like architects realize, that if you bend certain things, for example here, that if you have like a certain bending over there, then you can have far-reaching out like roofs, and like they are way more stable than if they are not bent, and it would be just straight. So that's one example of where curvature is really important and gives you stability. Okay, so that's, I think, like gives you some idea of why maybe you should care about like curvature and geometric objects and differential geometry. One more. Now we can start with like the boring stuff, namely some organizational stuff. First of all, if you have not joined the Canvas, then you can also here have the WeChat group. Just scan it and then join it. What is outdated? Ah, okay. It's then we will update it, and then on Canvas I put like the new code. Yeah, or maybe in the break we do that and like give you an updated course. Good. Then let's discuss a few more things. The first thing is our textbooks. Need that anymore? Okay, so the first topic I would like to discuss are like textbooks. So there are many textbooks on differential geometry. The one that I like the most and where the course will be mostly modeled after is by Neil. And it's called Elementary Differential Geometry. That's a quite nice book, which I like. Another one, which is like really one of the standard books, is by Docamo. And that's exactly the name of the course also. It's differential geometry of curves and surfaces. And one nice thing about this book is that you can also find this in Chinese. So there's an English version and a Chinese version. So if you prefer the Chinese version, you can go for that. And if you don't want to spend any money, which I really recommend, like you find either these books online, which you never heard from me saying, but there's also some lecture notes by Schiffrin, which are also quite nice, which I think are just called differential geometry. So these are the first course. So these ones you can just download for free on his website. And then there is a completely Chinese book, if you prefer, which is by Peng and Chen, which is also called differential geometry. So this one is also in Chinese. Yeah, so the book that I use the most is this one, but by no means you're like obliged to use either of these books. If you like look up online and you find like a book that you like and that like discusses the same topics, feel free to use that. It's like you're not required to have any of these books really, but they cover what we will cover in the course. I don't really follow it on the nose where I like really go chapter by chapter, but I kind of do like a bit of a mix of one from this book, one of that book. So then there's like this topic of homeworks. I think homeworks are really important. You can only learn mathematics if you really get your hands dirty and you have to calculate things. So the homeworks will be every week. I give out like certain exercises, and then you have to solve them and then upload your solutions to Canvas. And then yeah, the teaching assistants will correct them and then give you feedback. And that will be every week. I try to upload them on Thursday. And then you have 1 week time until Wednesday evening to solve them and to hand them in. And there are two kind of versions. One of them is like the great influencing one. So that's one part of the exercises where really you have to solve them, and like your performance on the solutions give you then 30% of the final mark. So it's like, yeah, like if you perform good on them, then you get like a good mark at the end. And there's a second time, which I call like exam qualifying. they are also corrected, and you also get feedback on how well you did. But it's not really important if you if you solved like 100% or 50. The important thing is that you need at least 50% to be admitted to the exam. So it's like you need at least 50% to be admitted. If you have like less than, then I will not let you do the final exam. So the idea behind that difference is that these ones are really examples that you really have to solve. These are like really essential things that are like really important things where I test you that you really know like the elements of the course that I talked about. These ones are a bit more tricky sometimes. They are like sometimes testing you in certain ways that you have not seen in a course or a bit more advanced. And sometimes it just happens that you can't solve these kind of problems. And that's okay, because there are certain problems that we all like and certain other problems that we don't like and that suit us better or not. So that will be part of that sometimes you will struggle solving these kind of things. You should not really struggle with them, but with them you sometimes struggle. And they're also a bit designed so that you struggle, and that's totally fine. And that's why I don't want to put them like related to your final mark, but they should be like you should have some motivation why you should learn and do them. So that's why I require at least 50% of them need to be correctly solved. And one more thing is like I really recommend you to work together. Like I think it's one of the most important things that you can learn in mathematics or in your studies in general is that you solve problems together. Like almost never at the end in like a company or in research, like you will ever have like a problem that you can solve completely on your own. It's always like that you work in a team. And I think it's really important that you learn that relatively early already during your studies. So if you find someone that sits now next to you and like will struggle with the same problems, just like reach out to them and say like, hey, I'm sitting Tuesday afternoon in that library place. If you want, you can join me and then we can discuss these problems together. So it's completely fine with me if you discuss problems together, if you solve them together. But everyone has to hand in their own solutions and not just like copy like the solutions of a neighbor, but really do them on your own. But yeah, you can like work together, and it's really important, and I recommend working together. Of course, there will be an exam at the end. I don't know yet the exact date. That will be like fixed at some point, and then I will let you know. It will be like the other part, namely 60% of your final mark will be coming from the exam, and you're allowed to use one sheet of paper. So one sheet of paper, like something like this, you can write on the front or in the back. You can use a computer or you can use like your hand to make notes. But like really just take one sheet of paper. Last time I had someone that was like really intelligent and glued 2 and 3 and 4 papers together. That doesn't count as one anymore. So please don't do that. Just like one sheet of paper. So that means like if you have some formulas which you really can't remember, and like it's also not so important to remember certain kinds of formulas, just copy them down and then go on. It's more like trying to test your understanding in the exam than just that you can calculate. Yeah, WeChat we just put on later again, and yeah, then there's will be exercise classes by Tong. I think he has proposals, namely the possible dates, and I think we just have like a quick vote on what kind of time suits you the best, and then I will ask the secretary to arrange like a concrete time and some classroom. So the options are, please correct me if I'm wrong, but it was Tuesday and Wednesday. So we have Tuesday, and then we have each one is afternoon, and something in the evening, and the same for Wednesday. Also afternoon and evening. So these are like the 4 options by the teaching assistant. So I would like to have a quick vote on just look up in your calendar when you have time, and then I will arrange that. So who has time on Tuesday afternoon? So it's one. It's only one? Okay, just raise your hand if you have Tuesday afternoon. Okay, it's only one. Okay. Who has time Tuesday evening? So it's 1, 2. Just raise your hand clearly, then it's better for me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. What about Wednesday afternoon? Wednesday afternoon. Okay. Okay, that's a lot. Just do a comparison. Wednesday evening. Okay, that looks less. So maybe I calculate Wednesday after 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's about 10 or 11. So it looks like Wednesday afternoon. And then I will ask the secretaries to arrange a room, and then let you know exactly where it will be and which exact time it will be. Okay. And okay, the final thing is about questions in the classroom. If you have any questions during, like if I say something and you can't understand it, like if you don't understand what I'm talking about, or if you just forgot something that I already told you, please raise your hand and just ask. Like, it's my job to help you make things understand. So if you have questions, just raise your hand and say, like, Professor, can you explain that again? It was like completely nonsensical what you just said. Like, it's totally fine. It's my job to explain it to you in a way that you understand. So if you have questions during the lecture, please ask. Also, that implies sometimes I just forget, like, to switch on the microphone, especially after the second part of the, after the break. So please tell me if I forget to switch on the microphone, because it's very easy to switch it on and just like raise your hand and say, like, Professor, your microphone. The same thing, sometimes what I write in the blackboard is not very readable. And if you can't read it, just raise your hand and say, can you write that again in a more clear way? Especially at the end of the lecture, I'm getting a bit tired and sometimes a bit sloppy. Really make sure that you really can read what I write. Yeah. Okay, that's, I think, all from my side about like the organization. Do you have like any questions for the structure of the course, or like also some of the motivational parts that I talked about in the first part? Okay, good. Then we can finally start with like the interesting part, namely mathematics. And today will be about curves mostly, so I will just talk about like a bit of like the introduction material, and that are curves. And there are like two ways to think about a curve. The first one is like essentially what I showed at the beginning already, is that you have some geometric object which is just like living in space or in a plane. So this would be something that you can think as a curve. But like all physicists know a little bit like a different viewpoint of a curve, namely that something that is like moving in space and is kind of like a particle that is moving with time and then traces out a curve. So there's these two different viewpoints of. One of them is like that you have like, a line which is traced out by a particle, like it could be also a virtual particle that you can think of, or really as like a geometric object. And it turns out that it's actually really like helpful to distinguish these two viewpoints. So the first thing is like what I would like to do is define what we understand as a curve. And for this one, we have that a parametrized curve. Well, there's one thing that I forgot to mention. I don't have like a script or some lecture notes, but I would like to have them at some point. So if any one of you is sitting here already with your laptops and like is thinking about tagging anywhere all of the material, please reach out to me. And and then we can maybe arrange that you give me the tag file afterwards, or I might even give you some money as a small reward for that. So if you're interested in taking all the lecture notes and providing them to me, that would be very grateful. Also, if you do that in a timely manner, then your fellow students would also profit from having some lecture notes to follow with. So that would be nice. Just write me an email if you're interested in that, or just afterwards the lecture come to me and say yeah, that would be something I would be willing to do. So that would be quite helpful if you want. So back to the curve. So a parameterized curve is like this idea is like that you have a particle that traces out some space. It's a smooth map. And I usually denote them by C, which is defined on some interval. So this one is some open interval or some closed interval. So it's a connected interval. Usually it's either something as some connected interval from A to B, or maybe from 0 to 1 or something like that. And the map is going to Rn, and for our course, n is usually 2 or 3. If it's 2, then I just say that it's a planar curve, so like a curve that is living in the plane. And we usually don't go higher than this, in this course at least. Yeah, and the picture that you should have in mind for this is that we have our interval that's usually living, so it's a subset of R, and then we have our map C that maps this one into a certain curve, and it maps a time point, like say t0, maps that to a certain point in space-time, which would be a C of t0. So that's a curve for us. It's like a map that assigns to a point, or like a time instant, the point where the curve will be. So you can really think of that as a particle that's traced out a certain curve in the space that we look at. So this one here would be say R2 now in this case. And once we have that, we all know from physics courses that we look at like the first and the second derivative, and that they are really important. The first one is that it's the velocity of the curve, and the second derivative gives you the acceleration. So the velocity, I usually denote derivatives by just like putting a dot above there, which is just the derivative with respect to the time direction of the curve C of t. And yeah, recall that, for example, just to make it really exact, that if you, for example, if you have like a curve in 2 dimensions, then we can write this as that we have a certain component in the first component, and yeah, like a curve in the second component. So it says like the x-axis is like a function of t, and the y-axis is a function of t. And if you have something like that, then the derivative is just that you take the derivative on each of these components. I think you have seen that already quite often in your course, but and as I said, second derivative is called the acceleration of the curve. And that's and all of them are, of course, then again, some vector in the same space. And then a curve, like that's like the parameterized version. And then the curve in itself is that we take the image of a parameterized curve. So, yeah, so that's really just like the geometric image that you trace out. So if you just follow that for all times, so image here means if that's new, it's like just like all the points. So it's all the points where the curve is defined. So it's just like a collection of points. So it's like in this picture here, that's a parameterized curve if you have like really a map that gives you the time to the point. And if you forget that map and just say like that's like a two-dimensional subset, then it's really like what we call a curve. And it will be important to distinguish a curve from its parameterization. That's why you have two different words. One is parameterized and the other one not. And why this is important will be coming here in a second. Just like as a very quick example, we all know that we can, for example, have the curve which is defined on the interval of 2 pi, and that sends t then just to sine and cosine of t. So that would be a parameterized curve, and that gives you a parameterization of the circle, of course. So the geometric object is the circle. And let's calculate the velocity and the acceleration for that example, just for completeness mostly. So the first derivative is minus sine t and cosine here, and then and of course the picture I think is familiar with is like we have here this map, and then this one gives us c of t, and then we have the velocity, which is a vector that goes, say, like in this direction, so that would be this vector, and the acceleration is like going back to the origin, so that's the acceleration of the curve. So that's a simple example. A bit more complicated example is the following. Do you think this curve fits into our definition? Do you think that's like a curve that we will look at according to this definition. The important part here that is that I already heard it. Someone said like smooth, namely that it's like the map that we look at that gives like the parameterization from the times to the points should be differentiable, and also should be the differential should be continuous and not jump around. So that's not a parameterized curve. If you look at that as a parameterization, say like if you parameterize that by x essentially, and then by y, so that would be for example, if you say like c of t would be a curve with t and then the square root of the absolute value of t. That if you plot that curve, it looks a bit like this one. And if you take the derivative of this, what you get is c dot. This one is just 1 here, but here you get 1 over square root of t, and then the sine of t. So that would be the velocity, but this one doesn't exist. At t equals 0. So if you plug in t equals 0, then the derivative doesn't make sense. And it also, like you can see this from this picture, is that like here it makes sense to talk about the velocity of the curve, right? But what is the velocity here? Like it doesn't really make sense to talk about the velocity. You go down and then up. But the important part is that it actually is, you can find a parameterization that has like a shape like this and is like a smooth map. So you can think about this for a second, and then I give you the solution. For example, you could try something like let's say we have a different curve. We could try, for example, something like this, which is like parameterized by a curve which parameterized by some parameter which I call S, and which has like a form like this. If you plot this curve, it looks very similar to this. It's not exactly with the square root, but the curve looks very similar. So in this sense, this one is a smooth map. If you take the derivative of this curve, you just get